So it says here design patterns and machine learning are like best practices, right? Kind of like a cheat sheet for common problems?
Yeah, exactly. They're basically tried and true solutions.
Hmm. So instead of reinventing the wheel every time.
Right. You leverage existing knowledge. Saves time and effort.
Makes sense. So like what kind of common problems are we talking about here? Is it like specific algorithms or?
Well, it can be anything from data preprocessing.
Oh, right. Data preprocessing. That's where you clean and prepare the data, right? Like handling missing values and normalizing features.
Exactly. It can also include things like model selection, or even how you deploy your model.
Deployment. Oh, like getting the model actually working in a real-world system?
Yup. Design patterns can help streamline that whole process.
So, this book is like a giant collection of these patterns, huh? Like Alexander's architecture patterns, but for machine learning?
Exactly. It's based on the same idea.
Hmm. I've heard of pattern language. It's like a way to describe common architectural solutions, right?
Right. Like, a place to wait, or wings of light. Describing best practices for design.
Oh, interesting. So, these machine learning patterns are kind of the same, but for like algorithms and data stuff?
Yeah. Like, how to handle imbalanced datasets.
Imbalanced data sets? Oh, that's when you have like way more examples of one class than another, right? Can skew your results.
Exactly. Or how to deal with, say, concept drift.
Concept drift? Ah, I'm not familiar with that one.
So,
So, concept drift is when the relationship between input data and output predictions changes over time. Like, your model becomes less accurate because the real-world situation it's modeling has shifted.
oh, I see. So like, a spam filter that becomes less effective because spammers change their tactics?
Exactly. Or a self-driving car's model needing updates as traffic patterns evolve.
Right. So these patterns, 253 of them, they cover stuff like that?
Yep. And they're presented in a way that lets you adapt them to your specific problem. Like, remember that architecture book?
Yeah, a pattern language. Light on two sides of every room, right?
Exactly. These machine learning patterns are similar. They offer a general solution, but you tailor it to your needs.
So, it's not just a copy-paste solution? You have to, like, understand the underlying principle and apply it?
So, it's not just a copy-paste solution. You have to, like, understand the underlying principle and apply it.
Right. Just like in architecture. Think of your favorite room in your house.
Probably my living room. Big windows, lots of light.
And your least favorite?
Ugh, the basement. No windows, kinda damp.
See? Light on two sides of every room. It makes a difference.
Yeah, I guess so. My living room does have windows on two walls.
And your basement? Probably not.
No, just one small, high window. Barely counts.
Exactly. These principles, whether for buildings or machine learning models, they reflect real-world best practices.
So, understanding those underlying principles is key.
Yeah. It helps you choose the right pattern and adapt it effectively.
Okay, so like with these machine learning patterns, understanding the why behind them is important.
Exactly. Just like understanding why light on two sides is good. It's not just about aesthetics.
Right. It's about, reducing glare and what was it? Being able to see facial expressions better?
Yeah. It's about the human experience. The quality of the light.
So, these machine learning patterns, they're kind of like design principles for good data models?
Precisely. They improve the quality of the model, so to speak. Make them more robust, adaptable.
Huh. So like one pattern might be about handling a concept drift?
Could be. Or dealing with imbalanced datasets. Or, ensuring data privacy. Lots of possibilities.
Imbalanced datasets? What's that?
Oh, it's...
Oh, it's when you have like way more examples of one category than another in your data. It can mess up your model.
Oh, okay. So, like, way more pictures of cats than dogs in a cat versus dog identifier?
Exactly. It can make the model really good at identifying cats, but terrible at dogs.
Right. Makes sense. So these design patterns, are they like rules of thumb? Like, light on two sides?
Yeah, kinda more like best practices drawn from experience. Like say, designing a balcony.
Balcony? What's that got to do with machine learning?
Well, think about it. How big should a balcony be? There's no one right answer, but there are good guidelines.
Okay,
Like 6 feet by 6 feet is good for a couple of chairs and a table, right?
subscribe to one patch code.
Okay, so 6 feet by 6 feet for a balcony. But how does that relate to like singleton?
All right. Singleton. Well, let me explain. It's a design pattern that ensures you only have one instance of a particular class.
Instance of a class? Ah,
Yeah, like, imagine a printer in an office. You usually only want one printer spooler, right? Not multiple ones fighting over the same printer.
right. One printer spooler. Got it.
The singleton pattern makes sure that only one instance of that spooler exists. Just like, ideally, you only have one connection to a database.
So, like one balcony per apartment?
Well, not quite. More like one central air conditioning unit per apartment. You could have more, but it's usually unnecessary and inefficient.
Okay. And proxy? Decorator? What?
Okay. And proxy? Decorator? What are those?
Right. So, these are other design patterns. Like singleton, but for different purposes.
Different purposes. Right.
Yeah. Think of decorator like adding toppings to a pizza. You start with a basic pizza, then add cheese, pepperoni, mushrooms. Each topping adds something extra.
Okay. So decorator adds functionality?
Exactly. Without changing the core pizza itself. In proxy, well, imagine a placeholder.
Placeholder?
Yeah, like an image icon that loads the full image only when you click it. The icon is a proxy for the real image.
So it stands in for something else?
Precisely. It controls access to the real thing. Like, a network connection.
Okay. So these design patterns, they're kind of like proven solutions to common problems?
So, these design patterns, they're kind of like proven solutions to common problems?
Exactly. Like recipes for software.
Right, recipes. So, this machine learning thing, is it getting more common?
Definitely. Becoming mainstream, actually. Like, used everywhere.
Mainstream meaning?
Well, like, used by lots of people in lots of different fields. Not just specialists anymore.
Okay. So if it's more common, are there like design patterns for machine learning too?
Yeah, absolutely. Tried and true methods for common problems. Like, dealing with messy data.
Messy data?
Yeah, like incomplete data or inconsistent data. It's a common problem.
Right. So, are these tried and true methods readily available?
Well, yeah.
So, TensorFlow, Keras, all those, they're part of this democratization thing?
Yeah, exactly. Making ML accessible to more people.
Accessible how?
Well, easier to use tools, more available resources, that sort of thing.
Okay. In this book, it's like a collection of these design patterns for ML?
Right. Like, best practices based on experience with those tools.
Best practices meaning?
Well, proven ways to solve common ML problems. Like, choosing the right model.
Right. Choosing the right model. So, like a cookbook for machine learning?
Exactly. A cookbook with, like, recipes for success.
So, if I'm starting with machine learning, this book would be helpful?
Definitely. It'd give you a solid foundation. Like,
Like a roadmap?
roadmap?
Yeah, like showing you the best routes to take.
Okay. So this transform pattern, what's that about?
Well, it's about managing the data you feed into your model.
Managing how?
It separates the raw inputs from the features used by the model.
Inputs and features. What's the difference?
Think of it like this. Input is the raw data, like say customer purchase history. A feature is a specific aspect of that data, like total amount spent.
Okay, so the transform pattern separates those. Why?
Right. And the transform is the process of converting the input into features, like calculating the total amount spent. The pattern makes these transforms persistent,
Persistent? Meaning?
meaning they're saved.
Okay, persistent. So what about this key predictions thing?
Yeah, that's for like batch predictions.
Batch predictions?
Yeah, like making predictions on a large data set all at once. Not one by one.
Like what? Give me an example.
Like say a recommendation system, predicting what millions of users might want to buy.
Right, okay. So key predictions helps with that? How?
It deals with efficiently distributing those predictions, like across multiple machines.
Distributing, meaning?
Well, imagine you have massive amounts of data. You can't process it all on one machine, right?
Right.
So you split the data and the prediction process across multiple machines. Key Predictions manages this distribution and joins the results based on.
Okay, distributing. So you mentioned SQL, scikit-learn, and Keras.
Right. The implementation code uses those.
I'm more familiar with SQL. What about the others?
Well, scikit-learn is a Python library for like general machine learning.
General how?
It has tools for like classification, regression, clustering, stuff like that. Lots of algorithms.
Okay. And Keras?
Keras is a high-level API for building and training neural networks. Often uses TensorFlow.
Neural networks. Those are for, like, deep learning, right?
Yeah, exactly. Deep learning is a subfield of machine learning. Deals with complex patterns.
So why provide code in all three?
Well, it caters to different needs and skill sets, like SQL for data pre-processing. So, this book talks about models and frameworks. What's the difference?
Well, a model is like the core algorithm that learns from data.
Learns how.
It finds patterns in the data to make predictions or decisions. Like, predicting moving costs.
Okay, so what's a framework then?
A framework is, like, a collection of tools and libraries that help you build and train models.
Like scaffolding for the model?
Yeah, exactly. It provides structure and pre-built components. Makes things easier.
So like TensorFlow and PyTorch are frameworks?
Exactly. They provide the infrastructure for building and training models. Keras can also be considered a framework.
So Keras is both an API and a framework?
Well, it's kind of both.
So, you're saying traditional programming uses if statements, right? For like, estimating moving costs based on rooms and size?
Right. Like, if 2 bedrooms and 2 bathrooms, then estimate is $1,500.
Yeah, I get that. But the example shows it gets complicated quickly.
Exactly. Like, what if there are 3 bedrooms and it's over 2,000 square feet? More if statements.
And more variables like furniture, clothes, fragile items.
Right. It gets messy. And customers might just give up if you ask too much.
So, machine learning can help with this?
Yeah. Instead of explicit rules, it learns from data.
Learns how? Like what kind of data?
Past moving jobs. Number of rooms, square footage, items, and the final cost. So we feed the model fast-moving data, like number of rooms, size, etc.?
Exactly. And the actual final cost of each move.
Right. So it learns the relationship between those factors and the cost?
Yeah, it figures out the patterns like, bigger houses generally cost more to move.
Okay. You mentioned feed-forward neural networks. What are those?
Well, imagine a network with layers. Data goes in one end, gets processed through each layer, and comes out the other as a prediction. Hence, feed forward.
Hmm. Like a factory assembly line?
Kinda, yeah. Each layer transforms the data a bit.
And you mentioned other models too, like linear regression?
Yeah, that's a simpler model. It assumes a straight line relationship between the factors and the cost.
Oh, I remember that from stats class. A line.
So, a line might not capture the complexity of moving costs, right?
Right. Like, a huge house with minimal furniture might cost less than a smaller, packed one. A line wouldn't catch that nuance.
So, neural networks are better for complex relationships?
Yeah, they can capture those nonlinear patterns. More layers generally means more complexity it can handle.
Okay, but how does it learn these patterns? What's happening inside these layers?
Well, each connection between neurons has a weight. During training, these weights are adjusted to minimize errors in the predictions.
Weights? What do you mean?
Think of them like, the importance of each factor. A higher weight means that factor has more influence on the final prediction.
So, like square footage might have a higher weight than, say, number of lamps?
Exactly. The model learns these weights from the data.
So, these networks are kind of like our brains?
Well, sort of. It's a loose analogy. They're inspired by the brain structure, but, they're not actually the same.
Right. So, how are they similar?
Like, both have interconnected nodes, like neurons in the brain, and connections between them.
And these connections, the weights, change as they learn, like how our brains form new connections.
Yeah, kinda. The network adjusts its weights to make better predictions, like how our brains adapt to new information.
So, the more data it processes, the better it gets at predicting, like learning from experience?
Exactly. More data, better learning, more accurate predictions.
But you said they're not the same. What's the difference then?
Well, for one, our brains are far more complex. Like, way more complex.
So, you mentioned deep learning. What's that about?
Oh, deep learning just means a neural network with multiple hidden layers.
Hidden layers?
Yeah, like, layers between the input and output layers. Think of them as intermediate processing steps.
So, more hidden layers means deeper learning?
Exactly. And deeper generally means it can handle more complex patterns. Like, way more.
Okay, so how do you actually build these things? Like code them?
Well, technically, you could code them from scratch.
Really?
Yeah, they're basically just math functions. But, nobody really does that.
Why not?
It's, like, super complicated. There are easier ways. Most people use frameworks.
Frameworks?
Yeah,
So, TensorFlow, that's one of these frameworks?
right. Probably the most popular one for deep learning.
Hmm. And you said open source?
Yeah, like, anyone can use it, modify it, distribute it. It's free.
Cool. So, TensorFlow is a library, and Keras is part of it?
Exactly. Keras is like, a simpler way to use TensorFlow. It's an API.
API?
Application Programming Interface. Basically, it's like a set of tools that makes it easier to write code.
So, Keras makes TensorFlow easier to use?
Yeah, it handles a lot of the, lower level details. You can build complex models with less code.
Got it. So, we'll be using Keras with TensorFlow?
Right.
Okay, so, you mentioned other frameworks besides TensorFlow?
Yeah. Like scikit-learn, XGBoost, and PyTorch.
Scikit-learn?
It's like, a general-purpose machine learning library in Python. Good for lots of stuff, but not really deep learning.
And XGBoost?
XGBoost is really good for, gradient boosting. It's often used for, like, winning Kaggle competitions.
Gradient boosting?
Well, it's a way to combine multiple decision trees to make a really powerful model. It's kind of advanced.
Okay. And PyTorch?
PyTorch is, like, another deep learning framework. Kind of similar to TensorFlow, but, some people prefer it.
So, TensorFlow, PyTorch, those are for deep learning.
So we'll use BigQuery.ml as an example?
Yeah, especially for like combining data pre-processing and model creation.
BigQuery.ml?
It's a machine learning service built into Google's BigQuery. You can build and deploy models directly within BigQuery.
So less moving data around?
Exactly. It's like more efficient.
Okay. And you mentioned data pre-processing?
Yeah, like, cleaning and transforming the data before training a model. BigQuery ML can handle a lot of that.
Right. So what about that diagram? It mentioned Vackerlarg.
Huh? Fakalarig. I think that's a typo. I'm not sure what that is.
Okay, weird. It also talked about different types of machine learning, like,
Linear models and decision trees.
right. Those are like, two different approaches.
Linear models?
Well, they represent patterns in the data using, like, a straight line. Or a plane, if you have more dimensions.
So like, y equals mx plus b?
Yeah, exactly. Simple, but, powerful for some problems.
And decision trees?
They're like, flowcharts. They make decisions based on the data, following different branches to reach a conclusion.
So, if this, then that?
Exactly. They can handle, like, more complex relationships than linear models.
So like choosing between them depends on the data?
Yeah. And, the specific problem you're trying to solve. Like, sometimes a simple linear.
So like, sometimes a simple linear model is enough, but sometimes you need something more complex like a decision tree?
Right. And, there are other types of models too, like, clustering models.
Clustering models?
Yeah, they, like, group similar data points together. Like, finding groups of customers with similar buying habits.
So, finding patterns without knowing the answer beforehand?
Exactly. That's called, unsupervised learning.
Unsupervised learning?
Yeah, it's when you don't have, like, pre-labeled data. The model learns the patterns itself.
Right. As opposed to supervised learning?
Uh-huh. Supervised learning is when you, like, tell the model what the answers are, and it learns to predict them. Like, showing it pictures of cats and telling it this is a cat. So, with supervised learning, you're, like, teaching the model?
Exactly. Like, showing it examples and giving it the answers.
And with unsupervised learning, it's, like, figuring things out on its own?
Yeah. Like, finding patterns in the data without being told what to look for.
So, like, with the clustering models you mentioned, that's unsupervised?
Right. It's, grouping similar data points together without pre-existing labels. Like imagine a scatter plot of points and the model circles the clusters.
Dimensionality reduction? What's that?
Well, it's like simplifying the data. Imagine you have like 100 different variables. Dimensionality reduction helps you find the most important ones.
So, like, throwing away the less important stuff?
Yeah, essentially. It can.
So, like, this book mostly focuses on supervised learning?
Yeah, because most real-world machine learning uses it.
Okay. And, it talks about, like, classification and regression?
Right. Classification is like assigning labels to things.
Assigning labels? Like what?
Well, like, is this email spam or not spam? Cat or dog picture? Assigning a category.
Oh, okay. So, like, choosing from a set of options?
Exactly. A discrete set of options. That's important.
Discrete set?
Yeah, like, distinct categories. Not a continuous range.
Right, right. And, what about regression?
Regression is like predicting a continuous value. Continuous value? Like what?
Um, like, predicting the price of a house. Or, the temperature tomorrow. Something on a scale.
Okay, so classification is categories, regression is scales.
Right.
So like with this data and feature engineering thing, what's that about?
Well, it's about preparing the data for the machine learning model. Like, getting it into the right shape.
Right shape?
Yeah, like, making sure it's clean and, has the right features.
Features?
Uh-huh. Features are, like, the individual measurable properties or characteristics of a phenomenon being observed. Like, if you're predicting house prices, features could be square footage, number of bedrooms, location, and stuff.
Oh, okay. So like the things the model uses to make.
So, like, the things the model uses to make predictions?
Exactly.
Okay. So, what about these, like, data sets? Training, validation, testing. Huh?
Right. So data sets are like the data used to train, validate, and test the model.
Train, validate, test? Sounds like, a lot of steps.
Well, yeah. Like most of the data is training data. That's what the model learns from.
Learns from? Like, memorizes?
Not exactly memorizes. More like, finds patterns. Then there's validation data.
Validation data?
Yeah, it's like, a check during training to see how well the model is doing. Helps prevent overfitting.
Overfitting? What?
Overfitting? What's that?
Um, it's like, when the model learns the training data too well. Like, memorizing it, instead of finding general patterns.
Oh, so validation data helps prevent that?
Exactly. It's like a, practice test. And it helps with choosing hyperparameters.
Hyperparameters? Sounds fancy.
Well, they're, like, settings that control how the model learns. Like, the number of trees in a random forest model.
Random forest? Is that like a type of model?
Yeah. It's a type of machine learning algorithm used for classification and regression problems. It uses multiple decision trees to make predictions.
Okay, so validation data helps tune these, hyperparameters.
Right. The performance on the validation data tells you when to stop training. Then there's test data.
Test data? So like another data set?
Yeah. It's like, the final test. After training is done.
Oh, so training, validation, then testing. Got it. But like, how do you split the data into these three sets?
Well, it's important that, like, all three sets have similar statistical properties. You know, like, similar distributions.
Statistical properties? Distributions? Sounds complicated.
Well, it means the datasets should be representative of the overall data. Like, if your data is about people, each set should have a similar mix of ages, genders, and so on.
Oh, okay. So like balanced data sets?
Exactly. It helps ensure the model generalizes well to unseen data. And, the data can take many forms.
Like what? Like, structured data and unstructured data.
Structured data? What's that?
It's like data organized in a specific format. Think spreadsheets. We also call it, tabular data.
Tabular data? Okay. So like rows and columns?
Right. And then there's unstructured data. Like, text, images, videos. Stuff that isn't neatly organized.
Oh. So like a mess?
Well, not exactly a mess. Just, not in a table format. More free form.
Got it. So, structured data is organized, unstructured data isn't. What about, like numeric data?
Yeah. Numeric data is like numbers, often used directly in machine learning models. Unlike, other data types.
Other data types? Like what?
Person B.
Like, categorical data. Things like colors, or, types of fruit.
Categorical. Okay. So like categories, right?
Exactly. And all this data, like, needs to be pre-processed before being used.
Preprocessed? What's that?
It means, like, getting the data ready for the model. We, call it feature engineering too.
Feature engineering? Sounds fancy.
Well, it's just, like, transforming the data. For example, scaling numeric values.
Scaling? What do you mean?
Like, adjusting the range of the numbers. So they're, comparable.
Oh, okay. So like, making sure one feature doesn't outweigh another?
Right. And also converting non-numerical data into numbers. Because, models need.
So, you're saying models need numbers?
Yeah. Like, they can't directly process red or apple.
Right. So, how do we deal with like an instance?
An instance? It's like a single data point. One row in your spreadsheet, or one, piece of unstructured data like an image or a text document.
Okay. So like one complete set of input data?
Exactly. And each instance is made up of, like, features.
Features?
Yeah, remember? Like, the process data. The columns in your data after you've done, feature engineering.
Right, the feature engineering thing. So, an instance is made of features, and features come from like raw data?
Exactly. The raw data is the input, like, the timestamp. And the feature is.
Right, the feature engineering thing. So, an instance is made of features, and features come from like raw data?
Exactly. The raw data is the input, like, the timestamp. And the feature is, well, the process timestamp. Like maybe, time of day.
Okay. So, what do we do with this instance then?
Well, we use it with a model, right? To, like, make a prediction.
A prediction? Like, what kind of prediction?
Any kind. Like, will a customer click an ad? Or, is this email spam?
Okay. So the model uses the instance to predict something. But how does the model like learn to predict?
With training examples. They're, like, instances with labels.
Labels?
Yeah, the correct answer. So like, yes, they clicked.
Labels?
Yeah, the correct answer. So like, yes, they clicked for the ad example.
Okay. So, a training example is an instance plus a label?
Exactly. Like, for the timestamp, the features could be day of week, city, and type of car.
Type of car? Why would that matter for a timestamp?
Well, maybe we're, like, predicting traffic congestion. Knowing the type of car might help,
Okay. So, the label would be what? The level of congestion?
Yeah, something like that. Or maybe, the average speed on a particular road at that time.
Right. So, the label is what we want the model to predict. And ground truth label?
Oh, that's just another name for the label in your dataset. Like.
Right. So, the label is what we want the model to predict. And ground truth label?
Oh, that's just another name for the label in your dataset. Like, the actual trip duration. So like, in our example, maybe 25.5 minutes.
Okay, 25.5 minutes. That makes sense. So, a float value, right?
Exactly. A float. Not, like, a category.
Got it. So we've got our dataset, features, instances, labels. Now what?
Data validation. Super important.
Data validation? What's that exactly?
Well, like, checking your data for problems. Making sure it's, good.
Good? Like, what kind of problems?
Lots of things. Like, data drift.
Data drift?
Data drift?
Yeah, like, when your data changes over time. So, like, the relationship between the features and label shifts.
Oh, I see. So, like, if people start driving electric cars more, our type of car feature might not predict traffic as well anymore?
Exactly. So, data validation helps catch stuff like that. We also got to check for, like, balance.
Balance?
Yeah, making sure we have enough examples of each feature. Like enough electric cars and gas cars in our dataset. It helps avoid bias.
Bias? Isn't that, like, a human thing?
Well, yeah, but our data can reflect human biases. If our dataset mostly has data from highways, our model might not predict city traffic well. Get it?
Right. So, balanced data, less bias. What if we can't get more balanced data? Then, we might have to use, like, special techniques. Like, oversampling or undersampling.
Oversampling? Undersampling? Whoa, those sound technical.
Yeah, well, like, oversampling means making copies of some data points to balance things out. And undersampling is, removing some data points.
Okay, so balance, bias, anything else to check for during validation?
Right. Consistency between training and test sets. Super important.
Consistency?
Yeah, like, you want your training and test data to be similar. Imagine, most of your training data is from weekdays, but your test data is mostly weekends.
All right. That wouldn't be a fair test, would it? The model would be confused.
Exactly. So we check for stuff like that. Making sure, the distributions are similar. So after training, testing, right? Model evaluation?
Yeah, exactly. Gotta see how it does on, like, new data, not the stuff it learned from.
Right. So like, a pop quiz for the model?
Haha, yeah. And, we might have to, like, go back and tweak things. Like, add more features or change the model a bit. Feature engineering and stuff.
Feature engineering?
Yeah, like, creating new features from existing ones. Maybe combining them, or, like, transforming them somehow. It can, like, really improve the model's performance.
Interesting. So train, evaluate, tweak, repeat?
Exactly. Until we're, like, happy with how it's doing. Then, we serve the model.
Serve? Like serving dinner?
Ah,
Well, not quite dinner. It's more like, making the model available to, actually do something. We use the term serving to refer to accepting incoming requests and sending back predictions by deploying the model as a microservice.
microservice?
Yeah, it's like a small, independent piece of software. Think of it as a mini program dedicated to just making predictions.
Okay. So, the model is live, taking requests, sending back predictions.
Right. The serving infrastructure could be in the cloud, on premises, or on device.
On device?
Yeah, like on your phone, or a sensor, or something. So the predictions happen locally.
Got it. So, what's this prediction thing you mentioned?
Oh, right. Prediction is just, like, sending new data to the model and getting its output. You know what the model thinks.
So, this prediction, it can be like online or batch.
Yeah, exactly. Like, online is for, quick predictions, small amounts of data.
Low latency, you said earlier.
Right. Low latency. Meaning, the time it takes to get a prediction is very short.
Okay. And batch prediction? That's for, like, lots of data?
Yeah, huge amounts. We're not worried about, like, speed so much there. It's more about processing a whole bunch of data at once. We're not serving individual requests in near real time, but processing data offline.
So, like, offline means not connected to the internet?
Well, not necessarily. Offline just means the predictions aren't happening live. As requests come in, it's done in a separate process, usually on a schedule. The data might still be stored.
So, batch prediction jobs, they take longer, right? Than online, I mean.
Right. Way longer sometimes. But, it's good for, like, pre-computing stuff.
Pre-computing?
Yeah, like, figuring out predictions ahead of time. Think, recommendation systems. Like, Netflix suggesting movies you might like. They don't do that live. Every time you log in.
Oh, right. That makes sense. So they pre-compute. Using batch prediction?
Exactly. Or, analyzing how the model performs on a ton of data.
Okay. So prediction is a good word for, predicting stuff like how long a bike ride will be.
Yeah. Or like, will someone abandon their online shopping cart? Stuff like that. Future stuff.
But for images and text, prediction seems a little weird. So if it's not really predicting the future, like with my bike ride, what is it doing with text then?
Well, it's still making an inference.
Inference? Like Sherlock Holmes?
Sort of. But not really. In machine learning, inference just means, like, the model is looking at the data and, drawing a conclusion.
So, concluding that a review is positive, that's inference?
Exactly.
So, prediction and inference, kind of interchangeable?
Yeah, pretty much. Though, inference is probably, like, more accurate for things like text analysis.
Okay. And you mentioned something about, training the model? What's that about?
Right. So, like, before the model can do any predicting or inferring, it needs to learn. That's training.
Okay. So training, you're feeding it data to learn from?
Yeah, exactly. Tons of data, usually. Like, labeled examples.
Labeled examples?
Right. So, like, if you're training a model to detect spam emails, you give it a bunch of emails, and each one is labeled spam or not spam.
Oh, I get it. So it learns the patterns. But what if you get, like, more data later on?
Well, you retrain the model. With the new data.
Retrain? So, start over?
Not from scratch, but, yeah, you kinda update it. Sometimes called, like, incremental learning.
Makes sense. But what if you're, like, constantly getting new data? Like a stream?
Aw, yeah. That's streaming.
Streaming, so like a fire hose of data?
Exactly. You need a way to handle that.
So, how do you, like, retrain with a fire hose? Don't you have to, like, stop the flow?
Not necessarily. There are ways to do it continuously.
Continuously? How?
Well, you can build what's called an ML pipeline.
ML pipeline? What's that?
It's basically, like, a multi-step system for, processing and analyzing streaming data. Think of it like an assembly line.
Okay. So the data flows through the pipeline and gets, like, processed at each step?
Right. One step might clean the data, another might transform it, and then another might retrain the model.
Huh. So, like, always learning?
Yep. Constantly.
So, all these products are serverless?
Exactly. We don't have to manage servers. Like, we focus on the ML, not the infrastructure.
Okay. So, like, BigQuery? You mentioned that.
Right. BigQuery is a data warehouse. Think of it like, a giant database for analytics.
Analytics, so like analyzing data?
Yeah. Big data sets quickly. It uses SQL,
SQL?
structured query language. It's like the standard way to interact with databases.
Got it. So, BigQuery is for data collection and feature engineering?
Exactly. Feature engineering is how we create the inputs for our ML models.
Oh, right. So, how's the data organized in BigQuery?
Well, it uses datasets and tables. Think of datasets.
Datasets and tables like folders and files?
Yeah, kinda. Datasets are like folders, and tables are like files within those folders. Like, organized storage.
Okay. So, you mentioned Google Cloud Public Datasets. What's that?
Well, it's like a huge collection of free datasets available in BigQuery. Lots of different stuff.
Like what?
Weather data, Stack Overflow posts, GitHub code, all sorts of public data.
Stack Overflow?
Yeah, like the website where programmers ask and answer questions.
Right. So, like, all that data is just there? Free to use?
Yep, ready to be analyzed in BigQuery. Good for examples and learning.
So, NOAA weather data. That's like historical weather information?
Exactly. Going back to, like, one?
So, NOAA weather data. That's like historical weather information?
Exactly. Going back, like, decades.
Wow. So, to build models using this data, we use BigQuery ML?
Right. BigQuery ML. It lets you build models directly inside BigQuery.
Inside BigQuery? So, like, without moving the data?
Yep. It's all in one place. Less hassle.
Okay. So, what's BigQuery ML exactly?
Well, it's a tool for building machine learning models from data stored in BigQuery.
Machine learning models, like algorithms that learn from data?
Exactly. And you can train, evaluate, and even use them to make predictions, all using SQL.
SQL again? So, like, I don't need Python or R.
Nope. You can do it.
So wait, TensorFlow models? What are those?
TensorFlow is a popular machine learning library. You can build complex models with it.
Library? Like a collection of code?
Yeah, exactly. Pre-built functions and tools for building ML models.
Okay, so you can bring those models into BigQuery ML?
Yep. Import them for predictions. So like, if you've already trained a model somewhere else.
You can use it with BigQuery data?
Exactly.
Huh. So, what's this cloud AI platform thing?
Well, it's, a suite of tools on Google Cloud for machine learning. More advanced stuff.
Advanced how?
Like, if you need more control over training, or, want to use custom models. Things BigQuery ML can't.
So, both BigQuery ML and Cloud AI platform support TensorFlow, scikit-learn, and XGBoost?
Yeah. All three. Gives you flexibility.
Hold on. Scikit-learn and XGBoost? What are those?
Well, scikit-learn is like a Python library for, like, simpler machine learning tasks. XGBoost is for, gradient boosting.
Gradient boosting?
It's, a powerful technique for building predictive models. Improves accuracy. Kind of complex.
Okay. So, custom containers? What's that about?
Right, so, like, if you build a model using, say, PyTorch.
PyTorch? Another machine learning framework?
Exactly. You can package it in a container and deploy it on AI platform.
So, like, it's a way to use.
So this book, it's for data scientists, data engineers, and ML engineers, right?
Yeah, primarily. Covers a lot of ground.
Okay. So data scientists, They're the ones who, like, wrangle the data?
Right. Collect, interpret, process, all that. Um, they do a lot of analysis too.
Statistical analysis?
Exactly. And exploratory analysis. Looking for patterns, insights.
So, they're involved in machine learning too?
Yep. Feature engineering, model building, that kind of thing.
Feature engineering? What's that?
It's like preparing the data for the model. Selecting, transforming, making it usable.
Got it. So what about data engineers?
Well, they're more focused on the,
Got it. So what about data engineers?
they're more focused on the, infrastructure. Like the pipelines and data storage.
Pipelines?
Yeah, like, the systems that move and process the data from source to destination.
Oh, okay. So data scientists use the data, and data engineers manage it?
Exactly. Data scientists work with the data in like Python or are often in notebooks.
Notebooks? Like Jupyter notebooks?
Yeah, exactly. For like interactive coding and analysis. Data scientists often build the first ML models.
Right. And machine learning engineers? They're like data engineers, but for ML models?
They manage the infrastructure and workflows around the models. Deployment, scaling, that sort of thing.
So ML engineers take the data scientists' models and make them production ready?
Exactly. They handle the, deployment, scaling, and all that.
Deployment? Like putting the model into a live system?
Right. So it can like actually be used. And scaling. That means handling lots of users or data.
Yeah. Making sure the model can handle the load. What about model versioning?
Well, that's like keeping track of different versions of a model. Like version control for code. So you can roll back if needed.
Oh, that makes sense. And serving predictions? That's like giving the model new data and getting results?
Exactly. Making the model's predictions available to users or other systems. Often through an API. API stands for Application Programming Interface. It's how different software systems talk to each other.
Got it. So,
So, you're saying one person could do all three jobs?
well, yeah, sometimes. Especially in smaller teams, or, early stage startups.
Right. So, like a full-stack machine learning engineer?
Exactly. Handling everything from data ingestion to model deployment. Ingest just means bringing the data in.
Got it. So, they build the pipelines, train the models, and deploy them?
Uh-huh. A lot of hats to wear. It can be, challenging.
I bet. So, how do you even become a full-stack ML engineer?
Well, you need a broad skill set. Data engineering, data science, and MLOps. MLOps is like DevOps, but for machine learning. It's about automating and managing the machine learning lifecycle.
MLOps, right. So like automating the deployment and,
So, like, automating the deployment and, what else? Monitoring?
yeah, monitoring, testing, and, managing the infrastructure. It's a whole thing.
Right. So, in bigger companies, it's less likely to find these full-stack ML engineers?
Exactly. Things get more specialized. You might have separate teams for research, data engineering, model development, and deployment.
So, like, a research scientist might develop a new algorithm.
Right. But they probably wouldn't be the one deploying it to production. That would be the ML ops team, or maybe a specialized ML engineer.
Makes sense. So what about data analysts? They use models, right?
Yeah, they might use existing models to analyze data and generate insights. But they're generally not building or deploying new models.
And developers? Where do they fit in?
Well, they might integrate ML models.
So developers, they integrate the models into, like, apps and websites?
Exactly. They take the deployed models and make them usable for end users.
Okay. So going back to research scientists, they're the ones pushing the boundaries of ML, right?
Yeah, exactly. They might explore things like hyperparameter tuning.
Hyperparameter, what now?
Hyperparameter tuning. It's like finding the best settings for a model, like tweaking the knobs until it performs optimally. It's a big part of model development.
Oh, okay. So like, finding the best learning rate or something?
Right, exactly. Or the optimal number of layers in a neural network. Things like that.
Got it. And they might also work on, like, model architectures?
Yeah, definitely. Designing new types of models. Or improving existing ones.
So data analysts, they're more about present insights, right? Working with existing data?
Yeah, exactly. They're like, detectives looking for clues in the data.
Okay. And they use tools like SQL and spreadsheets, right? And, business intelligence stuff?
Right. Stuff like Tableau or Power BI for creating visualizations and dashboards.
So they present their findings, like, with charts and graphs? To the product teams?
Exactly. To help them understand what's going on and make better decisions.
Whereas data scientists, they're more about the future? Making predictions?
Yeah. And, automating the insight generation. Scaling it up.
Automating how?
Well, like building models that can automatically analyze data and generate insights without needing a person to manually do it every time. Like automating the detective work. So, with like machine learning becoming more accessible, you think data analysts could become data scientists?
Yeah, totally. It's, definitely possible. They already have a lot of the skills.
Like what?
Well, like, data manipulation, right? And, understanding data. They just need to learn the modeling part.
Right. So like learning Python and some machine learning libraries?
Exactly. Stuff like scikit-learn or TensorFlow. It's, more achievable now than ever before.
So, what about developers? What's their role in all this?
They're the ones who, like, deploy the models. Make them available to users.
Deploy?
Yeah, deploy. Like, putting the models into production systems. So they can actually be used.
Okay. So they.
Oh, okay. So they take the model and, like, integrate it into an app or website.
Right. Like say, a recommendation system on an e-commerce site.
So what about these ML engineers? What do they do?
Well, they build the infrastructure like the, model serving infrastructure. That's what the developers use.
Model serving infrastructure?
Yeah. It's like the systems and tools that allow models to be used in real time, handling requests and generating predictions. It's pretty technical.
So, like, they make sure the models can handle lots of traffic and stuff?
Exactly. Scalability, reliability, all that. They're like the, plumbers of the machine learning world, making sure everything flows smoothly.
Okay. So, developers use what the ML engineers build?
Okay. So, developers use what the ML engineers build?
Right. And, the data scientists work with the data engineers.
Right, right. It's like a whole ecosystem.
Totally. So, you know how we were talking about all these different roles?
Yeah.
Well, like, there are a lot of challenges that come with all this.
Like what?
Well, data ingestion for one.
Data ingestion?
Yeah, it's like the process of getting data from different sources and putting it into a format that can be used for machine learning. Think, databases, APIs, stuff like that.
Oh, okay. So, getting the data ready to use.
Exactly. And then there's data validation. Making sure the data is, like, accurate and consistent.
Subscribe to one patch code.
Data validation? So, like, checking for errors and stuff?
Right. Making sure it's all, clean Because like bad data leads to bad models. Garbage in, garbage out, you know?
Yeah, yeah. Makes sense. So data quality is a big challenge then?
Huge. Like think about it, data drift.
Data drift? What's that?
Well, it's when the data your model was trained on becomes less relevant over time. Like customer behavior changes or the market shifts.
Oh, I see. So the model gets, like, out of date?
Exactly. It stops being accurate. And then there's like concept drift. That's similar, but it refers specifically to changes in the relationships between variables.
Concept drift. So, like, the way things relate to.
So like the way things relate to each other changes?
Right. Like, imagine you're predicting ice cream sales based on temperature. But then, like, a heat wave hits, and the relationship between temperature and sales changes because people stay inside.
Okay. So the model needs to be like retrained?
Exactly. And all of this, like, ties back to the data itself. If you train a model on bad data, you get a bad model.
Right. So like if the data is incomplete?
Yeah. Or, if it has poorly selected features.
Features?
Yeah, features are like, the individual measurable properties or characteristics of a phenomenon being observed. Think of them as, like, the input variables you use to train your model. Like, for ice cream sales, temperature would be a feature.
Okay. So bad features, bad model? So bad features, bad model?
Exactly. And then, like, there's the whole issue of data quality. It's not just about, features.
Oh, right. Like what else?
Well, like accuracy, for one. That's, how close the data is to the actual real-world values. Like, is the temperature sensor reading correctly?
Right, right. So like accurate data is important. Duh.
Yeah, well, it's more complicated than that. There's also completeness. That's whether or not you have all the data you need.
Completeness. So like no missing values?
Exactly. And then, there's consistency. That means, like, is the data formatted the same way everywhere? Are the units consistent? Things like that.
Okay, consistency. So,
Okay, consistency. So, like, after you collect all this data, you gotta, like, clean it up?
totally. Like, you have to do data cleaning or data cleansing.
Data cleaning?
Yeah, it's like, the process of detecting and correcting or removing corrupt or inaccurate records from a record set, table, or database and refers to identifying incomplete, incorrect, inaccurate, or irrelevant parts of the data, and then replacing, modifying, or deleting the dirty or coarse data.
Oh, okay. So, like, checking for typos and stuff?
Exactly. And, duplicates. Duplicate entries can really mess things up.
Huh? How so?
Well, like, the model might give too much weight to the duplicated data. It'll think it's more important than it really is.
Oh, right. Makes sense. So, like, just deleting the duplicates? Well, sometimes it's not that simple. Like, what if the duplicates are actually, slightly different? Then you might have to, like, merge them.
Merge them?
Yeah, like, combine the information from both entries. It can get, complicated.
Right. So, data cleaning. Then what?
Then, like, you have to think about the ground truth.
Ground truth? What's that?
It's like the actual correct values you're trying to predict. The absolute facts. The gold standard, so to speak. It's what you compare your model's predictions against.
Okay. So, like, if you're predicting, house prices, the ground truth would be the actual sale prices?
Exactly. And, like, your model relies solely on these ground truth labels and your training data to update its weights and.
Okay, so, like, ground truth. Got it. But what about, data completeness?
Right. Data completeness, huh? Well, it refers to, like, having all the necessary data, ensuring there's no missing information. It's, like, crucial for accurate predictions.
Huh. So like what if some data is missing?
Well, like, imagine you're training a model to identify cat breeds.
Okay.
And, you have pictures of cats, but for some pictures, you don't have the breed labeled.
Right.
That's incomplete data. Your model won't learn as effectively because it's missing information for some of the examples. Like, it's like studying for a test with, half the textbook missing.
Oh yeah. That makes sense. So like, what do you do? Just like delete the pictures with.
So like, what do you do? Just, like, delete the pictures with missing labels?
Sometimes. Or like, you could try to fill in the missing values. It's called imputation. But, yeah, it can be tricky.
Imputation. Right. Okay, so imagine we've got a cat breed identifier. Trained it on tons of cat pictures, 99% accuracy.
Wow. 99%? That's like amazing.
Yeah, but then we put it online and people start uploading dog pictures. And, well, it doesn't work so well with dogs.
Huh. So, like it's super accurate for cats, but fails on dogs?
Exactly. It's only trained on cats. It doesn't know anything about dogs.
Right. That's like a problem of scope. The model's scope is limited to cats.
So, like, it's only trained on 10 cat breeds. That's it. Its whole world is 10 types of cats.
10? Huh. So like what happens if you show it a picture of I don't know, a SPH cat? And it's only trained on like Persians and Siamese?
Right. It'll try to categorize it as one of those 10 breeds. Even if it's totally wrong. It doesn't have any other options.
Oh, so like it's forced to choose, even if it's a bad fit.
Exactly. It's like, a multiple choice test where none of the answers are right, but you have to pick one.
Right. So, it's not that it can identify other breeds, it just doesn't know they exist.
Yeah.
It may even do so with high confidence for an image that looks nothing like a cat.
Wait, really? Like, it could see a toaster and be like, yup, that's a Persian, 99% sure.
Well, maybe not that extreme, but yeah, it could misclassify something totally unrelated with high confidence. And, there's no way it'll say not a cat because it wasn't trained on that.
Not a cat. Right. Like, that wasn't an option on its multiple choice test.
Exactly. It only knows those 10 breeds. It's a problem with data completeness. Like the training data needs to be, well, complete.
Data completeness. So, like, what does that mean exactly?
Well, it means having all the necessary information. In this case, it means including examples of things that aren't cats and, okay, so like more than just different breeds of cats, you need pictures of whole cats. Like from the side?
Yeah, exactly. And, pictures of things that aren't cats too. Like toasters, dogs, whatever.
Right. So, the AI needs to know what a cat isn't too.
Exactly. And another thing is, like, if all your cat pictures are close-ups of their faces,
Ah,
then it might not recognize a cat from the side, or a full-body shot. It's a problem with, like, data representativeness.
data. Representativeness?
Yeah. Basically, your training data needs to represent all the different ways a cat can, look. Different angles, poses, the whole deal.
So like with the house.
So, like, with the house example, you need pictures of, like, all kinds of houses? Big ones, small ones, from all angles?
Right. And, inside and outside, different lighting, you get the idea.
Okay, yeah. So what about, like, if you have a ton of data? Like, way too much for one person to handle.
Well, then you probably have a team working on it. And that can lead to other problems,
Oh yeah. Like what?
like inconsistencies. Say, you're collecting weather data, like temperature,
Uh-huh.
with a bunch of sensors. But like, what if some sensors are in Celsius and some are in Fahrenheit?
Oh. Yeah. That would mess things up.
Exactly. Or say, you're labeling images of cats and dogs. Right. So like with the cat and dog pictures.
Well, say one person labels all the fluffy cats as Persian, and another labels them longhair.
Huh.
Yeah. So the AI gets confused, cause it thinks Persian and longhair are two different things.
Oh, I see. So it's like, labeling inconsistencies?
Exactly. It messes up the data. Like, if you're analyzing text sentiment.
Text sentiment?
Yeah, like, figuring out if a sentence is positive, negative, or neutral.
Right.
One person might label this as great, as positive, but another might label it very positive.
Hmm. So even small differences can mess things up?
Yup. Especially with, like, sarcasm. That can be really hard for an AI to understand.
Right. So like, how do you deal with that? With the inconsistencies, I mean,
Well, one way is to have multiple people label the same data.
oh, okay. Like, everyone labels the same pictures of cats and dogs?
Exactly. Then you go with the most common label. It's called, majority voting.
Majority voting. Okay.
Yeah. So like, if 5 people say positive and one says very positive, then it's positive.
Makes sense. So, like, what about bias? Like, labeler bias?
Ah, good point. Labeler bias is when someone's personal opinions affect how they label data. Like, maybe they think all small dogs are cuter, so they rate them higher.
Right.
Yeah, so you have to be aware of that. And, try.
Try to mitigate it. There are ways to, like, control for that kind of bias. We'll explore that more later. Like in Chapter 7. There's a fairness lens thing.
Fairness lens?
Yeah, it's like design pattern 30 or something. It talks about bias in more detail.
Okay. So, what about, like, when the data is collected? Does that matter?
Oh yeah, definitely. That's timeliness.
Timeliness?
Uh-huh. It's the delay between when something happens and when it gets recorded in your database. Say like an error in an app.
Right.
It might take a few hours for that error to show up in the log database. Or like with credit card transactions,
Yeah.
it could take a day.
Okay, so like, how do you deal with timeliness?
Well, you need to record lots of info about the data. Like when it happened, when it got logged.
Uh-huh.
And like make sure that time info is still there when you build your model features.
Model features?
Yeah, like the data you actually feed into your machine learning model. It's like the ingredients for the algorithm.
Right. Ingredients.
So specifically, you keep track of the timestamp, like when the event actually happened,
Okay.
and the timestamp for when it showed up in your database. So you have both.
Both timestamps. Right. So like, what if they're different?
Exactly. That difference is the timeliness issue.
Okay. So, how does that help? Having both timestamps, I mean.
Well, when performing feature engineering, you can account for these differences accordingly.
Feature engineering?
Yeah, it's basically like selecting, transforming, and creating relevant features from raw data. It's how you prepare the data for your model, like turning the ingredients into a recipe.
Right. Got it. So, you use the timestamps to, what? Adjust the data somehow?
Exactly. You can like normalize the data based on the time delay, or even create a new feature representing the delay itself.
Okay. So, what about reproducibility?
Reproducibility? Good question. In traditional programming, the output of a program is reproducible and guaranteed. You run the same code, you get the same result.
Right,
But with machine learning, it's not always so simple.
right. So how do you deal with that? The randomness?
Well, one way is to set the seed for the random number generator.
Seed?
Yeah, it's like a starting point for the random number sequence. If you use the same seed, you get the same sequence of random numbers.
Oh, okay. So if I use the seed 42.
Then I can use the same seed 42, and our model should behave the same way, yeah.
Right, right. So it's controlling the chaos?
Exactly. It ensures reproducibility. Imagine that banana example. With the same seed, even with randomness, the model will consistently misspell it if it has that bug.
Okay. So are there other ways to ensure reproducibility besides setting the seed? Yeah, totally. Controlling the initialization of the model weights is another big one.
Weights?
Right? The internal parameters of the model that get adjusted during training. They're initially randomized.
All right. So, if you don't control that randomness.
Exactly. You'll get different results each time, even with the same seed. It's like baking a cake. Even with the same recipe and oven temperature, slight variations can happen.
Okay. So how do you control the weight initialization then?
Well, you can, use specific initialization methods. There are a bunch of them, like Xavier or He initialization. They provide, structured starting points.
Xavier? He?
Yeah, they're, algorithms designed to set the initial weights in a more, stable and efficient way.
Right. So, if you don't use Xavier or He initialization or something like that, this can make it difficult to run comparisons across experiments?
Exactly. You wouldn't know if a change in performance is due to a change in your model or just random chance.
Okay. So, TensorFlow, that's like a machine learning library, right?
Yeah, exactly. And tf.random, well, that's, the part of TensorFlow that handles random number generation.
So, tf.random lets you set the seed in TensorFlow?
Yup. Just like we talked about before. It, ensures that the randomness is consistent across runs.
Okay, got it. So, setting the seed and using a good weight initialization strategy.
Yeah, those are, key for reproducible results in machine learning. It's,
So, just using tf.random.set_seed isn't enough? You mentioned something about scikit-learn.
Right. Scikit-learn also has its own way of handling randomness. If you're shuffling your data.
Shuffling?
Yeah, randomly reordering the data samples. It's often done before training. Scikit-learn shuffle function lets you set a random_state for that.
Oh, okay. So like a seed, but specifically for shuffling?
Exactly. So, you need to set both the TensorFlow seed and the scikit-learn random_state if you're using both.
Gotcha. So even with all that, there's still more to reproducibility? You said something about artifacts.
Yeah, well, think of it this way. Everything needs to be the same.
Okay. So everything needs to be the same. But how can the framework affect things?
Well, the framework is the underlying software, like TensorFlow. Right?
Right.
So, if the framework's code changes between versions.
Versions?
Yeah, like TensorFlow 2.5 versus TensorFlow 2.10. If the underlying implementation changes, even with the same seed, you might get different results.
Huh? Why?
Well, imagine, one version of TensorFlow calls its random number generator 13 times during training, and a newer version calls it 14 times. See?
Oh. So even if the sequence of random numbers is the same, a different number of calls will change the outcome?
Exactly. It's, like shuffling a deck of cards a different number of times.
Okay, that makes sense. So how?
So how do you control for that? The framework version, I mean.
Well, you need to specify the framework version you're using, like in a configuration file or,
A configuration file?
yeah, like a text file that stores all the settings for your experiment, so you can recreate it later. Chapter 6 talks about this, by the way. Reproducibility patterns.
Oh, right. Patterns. Like, blueprints for reproducible experiments?
Exactly. So framework version, seeds, data shuffling, it all goes in there.
Okay. But what about, like, distributed training? You mentioned that earlier.
Right. Distribution strategies. That's when you use multiple devices like GPUs to speed up training. Chapter 5 covers that.
GPUs?
Graphics processing units. They're like specialized hardware for parallel processing. Okay, GPUs. Got it. But with this acceleration, you said there's a challenge with repeatability? With distributed training?
Yeah. See, when you use multiple GPUs, the order in which they process data can affect the final result.
Huh. How?
Well, like, imagine each GPU processes a chunk of the data, right? And then they combine their results.
Right.
But if the order they combine the results changes, the final model might be slightly different. Even with the same framework version, same seed, everything.
Oh. So it's like, adding numbers in a different order? Sometimes you get rounding errors?
Kind of, yeah. It's more complicated, but that's the general idea.
Okay. So how do you, control for that?
Well, there are different distribution strategies, like, mirrored strategy.
Okay. So how do you, control for that?
Well, there are different distribution strategies, like, mirrored strategy, where, you basically duplicate the model on each GPU. Or,
Duplicate the model? On each GPU?
yeah, so they all process the same data in the same order. It's, like, the simplest approach.
Huh. Okay. But what about data drift? You know, the model gets trained on old data and then doesn't work on new data?
Right, data drift. That's a whole other can of worms. Basically, the distribution of the input data changes over time.
Distribution?
Yeah, like, the characteristics of the data. Think of it this way. Imagine training a model on 20th century news headlines, right?
Right.
It probably won't do well on today's headlines.
It probably won't do well on today's headlines. The language, the topics, everything's different. That's data drift.
So, like, the distribution of words changes?
Exactly. Today, we know an article with smartphone is about technology, but an older model wouldn't know that.
Huh. Makes sense. So you just, like, retrain it with newer data?
Yeah, basically, you continually update the training data, retrain the model, and adjust the weights assigned to different data groups.
Weights?
Yeah, like how much importance the model gives to certain features. Think of it as fine-tuning.
Right. So, like, with the storm data you mentioned? The NOAA thing? What's BigQuery, by the way?
Oh, BigQuery is a data warehouse on Google Cloud. It's where they store huge data sets.
So, like, with the storm data you mentioned? The NOAA thing? What's BigQuery, by the way?
Oh, BigQuery is a data warehouse on Google Cloud. It's where they store huge data sets, like massive.
Okay. So, like, all the storm data is in there?
Yeah, a lot of it. And if we were training a model to predict storms, we'd need to consider how reporting has changed.
Changed. How so?
Well, look at Figure 13. See how the number of severe storms reported has gone up since 1950?
Uh-huh.
That doesn't necessarily mean more storms are happening, just that more are being reported.
Oh, right. Because, like, better technology and stuff?
Exactly. More radar coverage, better communication. More people have smartphones to report weather events, too. So, um, like, how do you account for that when training the model?
Well, you could, normalize the data.
Normalize?
Yeah, basically adjust the older data to account for underreporting. You know, make it comparable to more recent data.
So, like, boost the older numbers?
Kinda. You'd use statistical methods to estimate how many storms likely went unreported back then.
Oh, okay. So, it's not just like throwing all the data in a pot and stirring?
Right. You have to consider the biases, the limitations of the historical data. It's complicated.
Yeah. So, like with Figure 13, what other factors could have influenced that upward trend? Besides, better reporting.
Well, climate change is a big one. Warmer temperatures can lead to more intense storms.
Right?
Right. So, with the radar thing, that's a pretty big change, huh?
Huge. Like before radar, storm data was mostly based on ground observations. Way less accurate.
So, what's exploratory data analysis? Is that, just looking at the data?
Well, yeah, kinda. It's like exploring it. Looking for patterns, anomalies, stuff like that. Helps you understand the data better.
Okay. So, you'd look at Figure 13 and see the jump in the 90s and be like, aha, radar.
Exactly. And then you'd know that data before the 90s is, well, different. Less detailed.
Right. So, you wouldn't want to use, say, data from the 50s to predict storms today?
Probably not. Unless you, only used...
Right. So, you wouldn't want to use, say, data from the 50s to predict storms today?
Probably not. Unless you, only used it after adjusting it. Like we talked about.
Right. So, what about when you have, tons of data? Really big data?
Well, then you have to think about scale.
Scale?
Yeah, how to handle massive data sets. Everything from collecting it to processing it to training the model. It can get really complex.
Oh, okay. So, more data isn't always better?
Well, more relevant data is better. But if you can't even process it, then it's useless.
Right. So, this bridge schema thing, is that about scaling?
Kinda. It's more.
Kinda. It's more about making different datasets work together, even if they're structured differently. Like bridging the gap.
Okay. So, combining data from different sources?
Exactly. Which, can help with scale, too. More data, if it's relevant.
Right. So, a data engineer would, build these pipelines?
Yeah, data engineers are the ones who build and maintain the systems that handle large datasets. Think millions of rows,
Whoa. Medial? So, that's where scaling comes in, right?
Totally. They need to make sure the pipeline can handle that volume.
And what about, training the model? Is that the data engineer's job, too?
Not usually. That's more of an ML engineer's responsibility.
ML engineer?
Yeah.
Yeah. A machine learning engineer. They're the ones who, build and train the actual models.
Oh, okay. So, image models? Those are different, right?
Totally different. Way more intense. They need much more powerful hardware.
Intense how?
Well, think about it. An image is thousands of data points, right? Compared to a row in a table.
Right. So, more infrastructure?
Exactly. Way more infrastructure. Specialized GPUs and stuff. Much more than four, tabular data.
GPUs? Like graphics cards?
Yeah, basically, but really powerful ones. They're good at parallel processing, which is what you need for images.
Oh, okay. So, what about model serving? Is that?
So, what about model serving? Is that getting the model ready for users?
Exactly. It's how you make the model's predictions available to, an app or a website.
Oh, okay. So, who does that?
Usually developers and ML engineers. They handle the scaling challenges, you know?
Scaling challenges? Like, what does that mean?
Well, imagine lots of people using the model at the same time. The system needs to be able to handle all those requests. That's scaling.
Right. So, like, making sure it doesn't crash?
Yeah, pretty much. And making sure it responds quickly. Nobody wants to wait forever for a prediction.
Hmm. So, like, even if a company isn't, super advanced with ML, this stuff still matters?
Totally. These ML.
Totally. These ML systems, even simple ones, need to be reliable and, reproducible.
Reproducible? Like, what do you mean?
Well, like, getting the same results if you run the model again with the same data. It's important for, debugging and stuff.
Oh, right. So like consistency?
Exactly. And it gets more complicated when you have, like, multiple teams using the same model.
Huh? How so?
Well, different teams might have different needs. Like, one team might prioritize speed, while another cares more about, accuracy.
Right. So like conflicting objectives?
Yeah, exactly. It's a balancing act. And then there's the whole thing about resilience.
Resilience? Like bouncing back from problems?
Exactly. Like if part of the system fails, the whole.
Okay, so resilience is like bouncing back from problems. But you were saying something about different teams having different ideas of what makes a model successful.
Right. Like, take a model that identifies defective products,
Uh-huh.
A data scientist might focus on minimizing cross-entropy loss. It's, a way of measuring how well the model's predictions match the actual data.
Cross entropy. So like how accurate the model is.
Yeah, it's a specific way to measure the difference between predicted and actual outcomes, often used in classification problems. But the product manager might care more about reducing the number of defective products shipped to customers.
Right. Different priorities.
Exactly. And then the executive team might just want to increase revenue like by 30%. Their focus is completely different.
So, the data scientist cares about the model's internal workings. The product manager cares.
So, the data scientist cares about the model's internal workings, the product manager cares about the actual product quality, and the executives just want more money.
Exactly. Each of these goals, they vary in what they're optimizing for. Balancing these different needs is tough.
Yeah, I see that. Like, how do you even start?
Well, as a data scientist, I could, translate the product team's needs into something I can use with my model.
Okay, how?
So, say false negatives are way more costly than false positives. Like 5 times more.
False negatives? Those are when the model says a product is good, when it's actually bad, right?
Right. And a false positive is when the model says a product is bad when it's actually good.
Okay, got it. So, bad products getting shipped are worse than good products being rejected. Exactly. So, I can adjust the model to penalize false negatives more heavily.
How would you do that?
Well, there are different techniques, like adjusting the classification threshold or using a cost matrix.
Cost matrix?
Yeah, it's basically a way to tell the model how much each kind of error costs. So, we'd assign a higher cost to false negatives. 5 times higher, like we said.
Oh, okay. So the model learns to avoid those more expensive mistakes.
Right. That way, I'm still working with my loss function, but I'm also aligning it with the product team's priority of shipping fewer defective products.
Right. So you're kind of translating their needs into the language of your model.
Exactly. It's about finding that balance. And then, we can see how that impacts the executive's revenue goals too.
So, it's like analyzing everyone's goals before you start building anything?
Yeah, exactly. It's like, proactive instead of reactive.
Right. So like design patterns?
Kind of. Design patterns are, well, reusable solutions to common problems in software design. Think of them as best practices, like templates.
Okay. So how does that relate to this?
Well, in this case, the problem is balancing competing objectives. By analyzing what each team is optimizing for, like a design pattern suggests, you can find compromises.
Hmm. So, like a design pattern for, organizational goals?
Yeah, sort of. It's not a formal design pattern, but the principle is the same. Codifying best practices, you know?
Right. So instead of just building something and hoping it works for everyone,
You figure out what everyone needs first.
and then you build something tailored to those needs.
Exactly. Like, this book talks about design patterns for machine learning systems.
Oh, interesting. Like what?
Well, it covers things like data quality, reproducibility, data drift scale, all the usual suspects.
Data drift?
Yeah, it's when the relationship between your input data and output variables changes over time. Like, your model gets less accurate because the real world shifted.
Oh, right. Makes sense. So these patterns help with that?
Yeah, they offer solutions. And they categorize them by the stage of the ML lifecycle.
Life cycle?
Yeah, like from initial problem framing to deployment and maintenance. Different stages, different patterns.
So, like, there are patterns for figuring out if a problem is even solvable with ML?
Exactly. It helps you.
It helps you avoid wasting time on unsolvable problems. The majority of patterns address either development or deployment.
Hmm, Makes sense.
And, quite a few patterns address the interplay between those stages. Development and deployment, you know?
Right. So connecting the build process with how it's actually used.
Exactly. Like, ensuring your training data reflects real-world usage. That's a common one.
Oh, right. So you don't build a perfect model in a lab that totally fails in the wild.
Precisely. Or, patterns for monitoring model performance after deployment.
So you can catch that data drifting?
Yep. Or, like, retraining strategies. That's another big one.
Retraining?
Yeah, like, when to retrain your model with new data to maintain accuracy. There are patterns.
Retraining?
Yeah, like, when to retrain your model with new data to maintain accuracy. There are patterns for that, too. Like, periodic retraining, or triggered retraining based on performance drops.
Triggered retraining?
Yeah, like, if your model's accuracy dips below a certain threshold, it automatically triggers a retraining process.
Huh. Smart. So it's constantly checking itself?
Exactly. Or, another retraining pattern is online learning.
Online learning?
Right. It's where your model continuously learns and updates itself as new data comes in, instead of batch retraining.
Oh, it's always learning. Real time, kinda?
Precisely. It's good for, like, situations where the data is constantly changing.
Right. Like stock prices or something.
Exactly.
So, are there patterns for how you retrain? Not just when?
Oh yeah, definitely. Like, there are patterns for handling imbalanced datasets.
Imbalanced datasets?
Yeah, it's when, like, you have way more examples of one class than another. Like, in fraud detection, you have way more legitimate transactions than fraudulent ones.
Right. So how do you deal with that?
Well, there are a few patterns. Like, oversampling the minority class.
Oversampling?
Yeah, like, duplicating the examples from the minority class to balance things out. Or, undersampling the majority class.
Undersampling?
Right. Removing some examples from the majority class. Or, using synthetic data generation. That's a more advanced one.
Synthetic data? Yeah, like creating artificial data points that resemble the minority class to balance the data set. It's, helpful when you don't have enough real data.
Oh, interesting. So like, you're making up data?
Well, not exactly making it up. It's more like, generating data based on the patterns in the existing data.
Huh. Clever. So like, are there any other patterns for handling imbalanced data?
Yeah, sure. Like, cost-sensitive learning.
Cost-sensitive learning?
Right. It's where you assign different costs to misclassifying different classes. Like misclassifying a fraudulent transaction as legitimate is more costly than the other way around.
Right. Makes sense. So you, like, penalize the model more for those mistakes?
Exactly. It learns to pay more attention to the minority class.